I'm Naman, and I'm here to sort of really go from the basics to sort of really go into how you can get an analytical understanding of the things that you're making. So sort of like, first go from like the very basics of like, what the forces would be and how you can really analyze that and see what is the impact of those forces. And then really working to how you can translate that knowledge into an FEA environment where you'd actually be able to simulate that and sort of, understand the different processes required to simulate it. Now, right now, this is actually, it doesn't require any software because this is sort of like, teaching you the universal things that are involved in FEA. And it's sort of like, going through being able to sort of build that intuition for, why certain things are strong and why certain things are weak. And I think sort of like the theme for this whole thing is, if I could sum it up in one word, it would probably be jugaad. And that's a very Indian term, but it's basically sort of, using the things around you in an unintended way to sort of make stuff. And that's basically sort of what's happened here. So I have a lot of demonstrations here. My table's just filled with them, and I'm really excited to show them all to you. And and the thing is that they're all very simple to do. They're just made out of stuff which you can find lying around at home. Most of these are just like paper and tape. And the idea is that, you guys can also make these, and it just becomes so much more interesting when you can see this kind of stuff from yourself rather than just, like if you're reading it somewhere or if you're just seeing someone else do it. So I think now that's basically a brief of what's going to be covered. And now I'll sort of just start. So I think to start off with, I have an interesting image. So I have this over here, and this is sort of, it was a slight meme on Reddit for a while. It was, the string is held up by constant stress. Now this sort of looks like one of those physics bending things, but it is very real, and I will prove that later. And so I think, does anyone sort of have any guess for like how this might work? Any sort of theories, any ideas that may come to mind? Right. I think people are right. Yeah.
I think everyone's
Yeah,
muted. Can
honestly,
people unmute themselves?
yeah, you can, like, honestly, this is really anyone's guess. That's sort of the whole point of this, to sort of see what all we could maybe think up.
Yeah, exactly. I believe anyone should be able to unmute themselves, so feel free. If you can't, let me know.
Yeah. I'll just give it a minute. Otherwise,
Voila.
I'll go through like a simple example and then actually see how that can sort of be moved up to this. So I think, sort of to start off with, let me just see. Is everyone able to sort of see the video here where I'm sort of showing a piece of paper and there's a Donald Duck ruler?
I can see it.
All right. Okay, great. So over here, I'm sort of going to show like a much simpler version of this. So if you can see here, I have what is basically a piece of string. All right. And over here, I have a ruler. Now, what's interesting about this ruler is that it's quite elastic. So if I sort of pull it back and I let go, it's going to spring back. Now, what's interesting is that if I pull it back and I bring this over here, and sort of, I've done a knot here so that it doesn't just release. You can see over here, I have this thing kept up, and from the bottom, I can hold it, and the string is taut. So what's happening is that this is constantly pushing out, whereas with the string, that's obviously overcoming gravity. So the string is sort of just being kept straight up by that. So this, I think, looks sort of familiar to what you guys might see as a bow and arrow. And this is exactly how it's done. So you sort of have a piece of string along a piece of wood, it's pulling on it, and that's how it's kept taut. And that's how you can sort of use that to shoot. Now, this is really sort of that just stacked multiple times. And luckily for you guys, I'm bold enough to make that. So you can actually see it over here. Now, let me see, I think it might be better. It might be more visible in my main thing. So
Awesome.
sort of like that. So if you can see, I've sort of created with these plastic pieces, each one is sort of trying to push outwards. And over there, they've used knots. Over here, I've used toothpicks just to, because knots ended up getting quite fidgety. But essentially what this does is it sort of prevents it from going any further. So you constantly have each one of these pushing it up. And since a string, so strings have very good tensile stress, which means they can sort of be pulled quite easily, but they have very low compressive stress. That's why it just falls if you keep it up. But in this case, everything's sort of pushing it up, so it's constantly under tensile stress, and that's how this stands. So that's sort of like, you know, the kind of stuff which I want to go through with this, and sort of go through, like, you know, all of these different ways to show things. So let me just spotlight this video. All right. So now, sort of to the part which I was talking about. So you have your tensile forces. Now that is sort of like me pulling on this. You can see it's quite strong. Nothing's really happening. Compressive forces are like, let's say, me pushing on this. Again, it's quite strong. Nothing's really happening. So these are sort of your normal forces, and then you also have shear forces. And shear forces is sort of like me doing this, and you can see it ends up breaking. So that is sort of something quite interesting to look at. And now we'll sort of work on a mathematical understanding of that and how you can really translate that into simulations. But I think before that, I sort of have here a triangle, and here I have a square. Now, I think a lot of you guys would know, if I have to say which shape is the stronger shape, which one would you guys say? You can just sort of tap out the answer in chat. This is sort of like your...
Triangle.
Triangle.
Yeah, yeah, exactly. It is definitely the triangle. But I think, would anyone know why it's the triangle?
It's kind of a resistance to creating moments that can kind of bend it. They all
Yeah.
assemble in the same point.
Yeah, that's quite good. So yeah, it sort of comes down to where your forces are. So you'll sort of see with this, I can actually sort of, when I push on this, the whole thing can turn. Whereas over here, when I push on it, nothing really happens. All of the force is sort of being directed along the beams. Whereas over here, it can be directed along one of the diagonals where there is no beam. And that's why you have that the triangle is always the strongest shape, because I can't make any connections to the corners without it crossing a beam. That's why it's so strong. And you sort of see that it really comes down to your shearing versus compressing. And that's something which we're going to look at now. So over here, let's say I have just, you know, an unsuspecting square. So now with a square, let's say it's sort of made out of aluminum, and I'm just going to pull on it here. So now if I'm going to pull on it, what happens? Well, what happens is that the entire square will just move to the right, or I guess for you guys downwards. Um, so that's sort of what would happen if I just applied one force. So that's why you sort of always see two forces being applied. Unfortunately, everything is inverted 90 degrees. Think if I do this, it might go better. There we go. It's going to be a bit hard for me, but let's see. I can probably work with this. Okay, yeah. So over here, let's say, you know, let's just randomly have the force be like, let's say 5 newtons here and 5 newtons here. So now what happens is that you have two forces here. It's in translational equilibrium. This is, you know, your high school physics that you've done. Now what you'll actually see happening is here. So you will actually sort of see the whole shape deforms slightly. And over here, we are going to describe this deformation. So you'll sort of see that the shape actually deforms, and we're going to talk about how we can really use that deformation. Now I'm sure, unfortunately, I actually don't have a rubber band right here, but I'm sure if you guys have ever pulled a rubber band, you can sort of see that it deforms so much. So just from pulling on it. So now we're actually going to see how deformation works. So what happens is that you want to look at deformations in terms of stresses. So let's say if I'm putting a force here, I actually don't want to think of this in terms of a force. That makes things complicated. So you want to, like the whole concept of mechanics is actually non-dimensionalizing. So what that means is that let's say if I have a force over here of let's say X newtons, and it is pulling on a surface with a cross-sectional area of, let's say, y meters squared, then you would actually think about it in terms of the stress. Now the stress, which I would use sigma to identify sigma, let me just write stress. Stress is equal to your force upon area. So force upon area, which in this case is equal to x upon y. Now, one question that I get asked a lot is, what is the difference between stress and pressure? Because isn't pressure force upon area? And yeah, so pressure is force upon area, but the main difference is sort of how we use it. So with stress, you'll sort of see later, you have different examples of how stress is acting on a body where pressure cannot. And another thing you really look at is stress is sort of talking about what happens internally with the body. So you're not actually looking at the force you're applying to the body, you're actually looking at the internal force which the body is pulling back with. And that force will always be the same. So it's just easier to think about it in terms of the forces you're putting on the body. So here you actually have a definition for stress. So that's quite simple. Now, how do you do strain? So strain, which you would write as epsilon here. Epsilon is your strain. So with strain, let's take a look at this thing again. So let's say this is X, and let's say this thing over here is delta X by 2. So the total, so the old length over here is equal to X, and the new length plus delta X, right? And I promise we'll be done with the boring math soon. So over here you have a description for the old length and the new length, and your strain is actually equal to delta X over X. So you're actually looking for the change in length. So you're looking for the difference between the old length and the new length, and you're dividing it by the old length. So that is how you get the strain. Now this is useful, but with a simulation, you only know the forces. You don't know the effect of the forces. I mean, if you knew the effect, why would you be doing the simulation? That's just waste of time. So there's actually a relationship between stress and strain, and that's Hooke's law. And that is that your stress is equal to Young's modulus into strain. And so let me just sort of nicely label this. So now you guys are familiar with what stress is and what strain is, but you're not really sure about what Young's modulus is. That's a new one. So Young's modulus actually is sort of an inherent property of the material. And Young's modulus is basically determines the elasticity of the material. So let's say something with a very high Young's modulus means that I would need to, pull it a lot to see any kind of deformation, whereas something with a low Young's modulus means that you really wouldn't have to pull much to see that deformation. So for instance, like I can give some values with aluminum, the typical Young's modulus value is 68 gigapascals. Let's say with steel, it ends up being around 130 gigapascals. So you can see these are some really large values. And if you actually look at this with stress, with the relationship between stress, Young's modulus, and strain, you see that unless the force you're applying is really, really huge, your strain is actually going to be very low. And that's true. The typical strain values you'll end up having are something like, so here's actually typical. Let me just essentially modular and your typical strain values end up coming to, approximately, like let's say 0.001 or so. So you actually deal with like really low orders of magnitude. And that's why, like let's say if I just, like pull on my steel bottle, you're not going to see anything because well, unfortunately I'm not that strong. But yeah, so that's sort of where you'll see deformations happening. Now, deformations are good and all, but you want to sort of see what does a deformation mean. So over here, I am actually going to sort of plot a curve. This curve is known as your stress strain curve. So this would be your stress, and this would be your strain. And your typical curve looks something like this. So sort of be like that. This over here. So you have a couple of key points. You have this point over here. You will have this point over here. And then you have this point over here. So does anyone have any guesses about what each of these points means? Just any guess you guys can?
Yeah, one guess is that leftmost point is a point of the von Mises stress where you are the end of the elastic region.
That's right. So this is your limit.
And I guess that's also the limit for where the Hooke's law is appropriate, right?
Yes, that is exactly true. So over here, if you sort of see your gradient, so you would have your gradient is equal to, and that is only true for this region. Because as you can see over here, you no longer have that constant gradient. So in fact, if you sort of want to be a bit more technical, you can actually look at later points where, in fact, over here, you actually have a variable Young's modulus, but that's sort of something that you don't really have to worry about. But yeah, that is sort of something interesting. Now, I think some of you guys can probably guess what this X point is. Anyone?
Here it probably breaks.
Yep. So that is your fracture point.
And the one in the middle is a absolute stress limit.
So yeah, so this is sort of the high stress it can take. But there's a very interesting name for what happens here. It's called necking. So what's interesting about necking is that now this is called a stress strain curve, but what it actually sort of measures is, let's say you have machines which can sort of put a lot of tensile stress. So you would essentially, the machine would actually be measuring the force, and you just divide it by the area to get the stress. So what actually happens is at your necking point, because logically this really doesn't make sense. Um, how could it be that, let's say, if I sort of keep my stress at a constant value, it'll suddenly start breaking? That doesn't work. It shouldn't just elongate even more if I just leave my force constant. And that's the thing. That is, in a perfect world, that would actually never happen. But what happens is that we live in an imperfect world, and that is why this always happens with anything. So it's that, let's see what I'm pulling on this. Right? So this is the beam which I'm pulling on. And at the necking point, what happens is that sort of chunks of material come away over here. And this is of course going to be where my fracture is. And if you can see this length, let's say, let me make this X and let me make this Y. So X is clearly less than Y. And what that means is that the area at X is less than the area at Y. And since we know that your stress is actually the force upon area, what happens is that if you're decreasing the area, you're increasing the stress. So that means that you actually have a higher stress even though the force remains constant. And that's why you get this point where even though your force is staying constant, your stress is actually increasing. And that's why you get to here where you need to actually decrease the force if you want to prevent it from fracturing. So, the limit of elasticity is like this is like the point you probably shouldn't cross.
Yeah, if you don't want permanent, what do you call it, change.
Yeah, this is the point you definitely shouldn't cross. And this is your start over region. So yeah, that's sort of a fun way of remembering. But yeah, that's very important. You don't want to have, you don't want to deal with any permanent deformations. So what actually happens is, I'm not going to draw it here because it gets too crowded. But actually, at any point, if you stop loading, it'll actually sort of come back in a straight line with the gradient of the Young's modulus. So that means that obviously if it's within your elastic region, it'll just come back to zero and you will have an undeformed body. But let's say if it's sort of out here, it'll be coming back here. So you can still see there will be a slight permanent deformation. And that means that, like, let's say if you keep on loading and unloading, that is something which you don't want. Although, in certain edge cases, if there is something which you like only plan to use like once or twice, then it might be okay to do that. But please don't call me up if it breaks. I don't really sort of vouch for that. So these are your normal forces. But I think, as you guys saw with that demonstration, normal forces really aren't the things you need to be worried about. Because over here, I couldn't break this by pulling it. I couldn't break this by sort of compressing it. I could only break it when I just snapped it. And snapping is what is your shear force. Now, shear force is a bit more annoying to show. So let's say if I have something over here, this. Okay, so shear force essentially means it's acting parallel. So let's say, I might be sort of pushing this up from here. Now, as you guys remember from the previous diagram, if I sort of push it up from here, the whole thing will just go up. All right then, so since it needs to be parallel, I guess I'll sort of push it down from here as well. All right, that's cool. But no, that's not enough. Now it's going to rotate. So that means I actually need to sort of push it here and push it there as well. And that's sort of where it gets a bit complicated. And this, it seems very complex, but this is the kind of thing which you don't even think about. Like, let's say if you have like a sheet of paper, or in my case, if you have this sort of stirrer. Now I'm not just pushing this up and pulling this down. What I'm doing is I'm using my thumb as a pivot. So I'm actually sort of creating that force where I'm keeping this in translational equilibrium here, and then I'm pushing up from here, which causes it to break. So, now we're sort of breaking that down in terms of forces. So again, over here, all of these forces are constant. And let's say if this is your XY plane, this is your X, this is your Y, your shear forces are tau. So this would be tau X, this would be also be tau X. This is probably not ideal in a 2D example, because you would actually sort of see these forces in a 3D example where you would have sort of like X, Y, Y, X and all. So this is here. And you'll note that tau X is equal to tau Y. So let's give some more examples of shearing, because honestly, like for me, shearing was just this very weird thing which I could, like, it honestly took me a long time to get my head around, because it's so weird to think about. You don't really think about things that way. So I found that the best example is actually a book. So right here I have a math textbook, because why not? So if I try to sort of compress this textbook or pull it again, you can see not much happens. But now let me see. If I try to sort of shear it, so I'm sort of pushing it along from the top only, you can sort of see that the pages here slide over. It's a bit, it's not very visible, but you can sort of see over here that that these pages are sliding over. It's coming at some kind of angle. So now I can actually describe that. So if I look at my deformed body, let's not make it on the same diagram. So this is my deformed body. So, all right. And now over here is your length. So this was your original length of the body, and this is your deformation. So let's call this delta X. So now we need to figure out how we're going to measure the shear force. So, all right. So let's say your shear force, your tau, is equal to delta X. All right, seems reasonable. But wait, okay, let's say if I measure it from here, now delta X is a lot smaller, but the force is still the same. If I had an object that was sort of half the height, that means my strain is somehow less. My stress is somehow less. But we remember that stresses actually don't are sort of constant no matter what the dimensions are. So that means it can't be this. Now, what we can actually realize, the one thing that's constant here is actually this angle. So the angle can actually be taken as, so you actually take it as delta X over L is equal to the strain. And if I call this angle theta, this is also equal to tan theta. If you guys remember SOHCAHTOA, this is your opposite upon adjacent. So this is how you describe your strain, and the symbol for that is gamma. So gamma is your strain. Let me just specify shear. And again, the same relationships apply. So you know that this is sort of delta x over L. You know that this sort of tau, which is equal to your force upon area. That remains constant. It's just that the force is being loaded in a separate direction. The area still stays the same. This would be the 3Q. So this is your force upon area, which is equal to shear stress. All right, so now onto the relationship between them. So tau is equal to Young's modulus tau. No, wait, that doesn't look right. So the thing is that, you know, with your compressive and tensile forces, you sort of saw that they were more or less the same. So you could actually describe them with Young's modulus. In this case, you can't use Young's modulus. That's wrong. You have to use this, which is the shear modulus. So G is your shear modulus. And let's just rewrite this. So tau, which is shear stress, is equal to so this is sort of your relationship. And one thing that's very neat is that you can actually, there is obviously this isn't something that applies for absolutely everything, but generally, like as a rule of thumb, you can say that your shear modulus is approximately equal to your Young's modulus divided by 3. And this is why shear forces are actually the ones you need to be afraid of. Because shear forces, if you can see as G becomes smaller, that means your strain actually increases while the stress remains constant. So you actually want a modulus that's large. And that's why shear forces are the ones that you need to be afraid of. If I just sort of take a sheet of paper, you know, by pulling on it, I mean, I could break it, but like it's unlikely, and obviously not by pushing on it. But if I tear it, it's very easy. And that's where your shear forces come into play. You really want to avoid shear forces. And now we can actually go back to this example over here. So the thing is that now what I'm actually doing here is I'm applying a load parallel to this face, which allows it to get sheared. Now, the thing is that over here, if I'm applying a load parallel to this face, that sort of just ends up being normal to in other sense. So you actually just can't apply, you really can't sort of effectively apply shear forces here. You know, like I'm really trying. The only time this sort of bends is actually when the rod itself bends, and that shows how strong triangles really are. And honestly, this is something which I would highly recommend making. It's just like, you know, any kind of story you can find at home. Really anything you can make this. And it just allows you to so like, you know, visually see the difference between the forces. And now I think sort of the final and probably the most cliche example that you have of these forces is, and let me just grab, so here. So like, let's say if I have this sheet, now with scissors, if you sort of see, these faces aren't actually aligned. So if I sort of do a diagram of scissors, it's not like this, it's actually like this, where they sort of offset from each other. And that is why they're actually able to shear it. Because if you see, they're making the area very, very small, and that's what allows scissors so effectively to cut. But one thing to note is that scissors are actually just applying this upward and downward force. The thing is that they're just taking advantage of leverage so that they're actually able to cut. because you're assuming that that the material will reach a breaking point before it actually turns. Now that isn't always the case. So over here I have these slightly blunt scissors, and I sort of try to manipulate this as much as I can. And sort of, if I do it just right, hopefully it doesn't cut. And if you see like this, you sort of get this kind of situation where it gets stuck in between the scissors. And that's because this whole thing has just rotated and that's sort of gotten stuck in here. And that's why scissors don't always work. So that's sort of something which, I'm sure you guys would have had situations where with scissors, you've, like, it's just not been able to cut an object. And that's exactly why. All right, so now we get to some of the fun stuff. Now, sort of very quickly revisiting this, you can sort of see over here when I showed here, not only is this stretching, this is actually shrinking slightly. And it's shrinking because of this thing called Poisson's ratio. So Poisson's ratio actually describes the relationship between the contraction on the other axes and sort of the extension in one. So what's a bit annoying is that the symbol for it is sort of this. It's not velocity. I mean, people are bad at sort of giving symbols to things. Now, what's really easy is that if I sort of look at strain, so like let's say a strain in the x direction, I can actually sort of see that is equal to negative Poisson's ratio times the strain in the y direction. So this actually allows us to sort of go to three-dimensional cases, because now you know that this force here gives you a certain strain in the x direction, and you can use your Poisson's ratio to find the strain in the y direction. So in this case, because you want to know why, it would sort of be like this instead, where you're taking the known one and you're using this to find the unknown. And if you actually wanted to find the strain in Z, in this case, which is the one you can't see on the paper, which is also equal to this. This is assuming that the material is isotropic. Isotropic is just a fancy word for saying it's the same in all directions, which is like, if you guys are familiar with the grain, with like, wood being a grain material, you know that it's stronger if you put forces on it. Like, let's say if you're working along the grain, wood is much weaker. Whereas if you're working against the grain, it's a lot stronger. So that's sort of where anisotropy comes along, but you sort of don't really need to worry about that for the understanding. But yeah, so if you're using anisotropic materials, you'll have to sort of specify that in your analysis. So over here, this actually tells us Poisson's ratio. And the reason it's negative is because if you see over here, an extension leads to a contraction. So that's why this just allows Poisson's ratio to be a positive number. Now, I hope at least some of you are wondering, well, what if Poisson's ratio is a negative number? Is that even possible? And to that, I show you this. So this is called the herringbone tessellation. And if you see, if I actually, like, as I pull this along, it sort of expands outwards. So this actually has a negative Poisson's ratio. So it's a bit cheaty. I mean, I'm using origami here, but origami actually has very interesting applications in engineering. That's something I'll come to. So this is sort of like, one of those really cool ways to sort of show some like, exceptions to the rule, where this would actually have a negative Poisson's ratio. And this is something which you can this is just a sheet of paper that's been folded. You can check out YouTube tutorials on this, although I would not recommend it. It is a pain to make. We had a blackout in my city, like just all the power went out. So I was bored and I just made this. So I thought, why not? And now you guys may be thinking like, what is the real world use of this herringbone tessellation? And this sort of isn't one, but to that, I give you this. So this doesn't look that impressive right now, just a sort of folded sheet of paper, but this is actually called the Mura fold. And this is sort of another example of negative Poisson's ratio, but it has some really cool applications. So if I just pull on my fingers here, you can see the whole thing expands out into a sheet of paper. And what's really cool is that I can sort of just compress it down back. really easily. So what this allows me to do is just with, I'm literally just putting, like I could just sort of have this be still. I'm just putting one force and the whole thing is coming up. And this is actually what is used by NASA in space applications for deployable solar panels. You'd actually have solar panels on each of these things. You'd have the entire thing folded up and it would be sent to space like this. You'd have a single motor that just pulls it out, and then suddenly you have a gigantic array of solar panels that's bigger than the shuttle itself. It's really cool, and I would highly recommend making this. It's quite simple, takes about 20 minutes, and it's just, I mean, it's really fun to play around with. It is, it never gets old. uh, so that's called the Murafold, and it has really interesting applications. So that's sort of just showing where you're looking for like sort of exceptions of the rule for interesting occurrences. You can get these sort of crazy applications. So that's sort of like, something that I thought was really interesting. So yeah, I think that's sort of like the basics that I've got for your different forces and all, and this should give you that understanding of like, like let's say if I were to sort of try and compress a block, like a metal piece, how would I calculate that? And then obviously this in later, once you get to more complex examples, it could be, you could bring it to, let's say if I have a building and if I have wind force acting on the very top of that building, how much is that going to shake? So yeah, I think right now I sort of want to sort of take a slight pause and just check if anyone has any questions, anything else, or otherwise then I can actually sort of move on to how you'll be bringing this into simulation software and actually using that. So yeah, I think
I have a
any
quick
question.
question. Just what was the
Mhm.
name of that fold again? I tried to Google it just now and came up empty.
Yeah, wait, let me actually just double check to make sure my spelling is correct. Um, all right, yeah. So it is Mira fold, and the other one is,
Ah, Miura. Okay, cool. Thanks. Beauty.
yeah, the other one is herringbone tessellation, although it's like a lot of effort. I actually had a friend who tried doing the herringbone tessellation, and yeah, I think she attempted it like 3 times and then just gave up.
You need to
So
make a
yeah, it's
machine that can do that.
I honestly, I would not be surprised if there were machines like that. It's, yeah, but the herringbone tessellation, it looks a lot more intimidating. It looks a lot more fun than the other one. 3D printing. 3D printing would be interesting, although I'm not sure if you can get that level of flexibility with 3D printed materials. The one interesting other thing which I would like to show that we can actually is this. Just reload it real quick. This is the impossible table. So if you can see over here, now I would like to see if someone wants to take a shot at explaining this. These are all just pieces of string. There's no sort of like editing magic going on here. Would anyone sort of like understand how on earth is this staying up? And then I'll show you guys my terrible recreation of it.
Yeah, I think for the people who came in late, you might want to show them that thing with the string too. But
Mhm.
So I think here it's the secret is this small little string in the middle, right? That like pulls the top one up. Yeah.
Yeah, that's exactly it. So yeah. So do you want to sort of elaborate on that?
No. I mean,
Just go for it. I mean, honestly, like guesses are great. You get to a lot of stuff from guesses. So yeah,
Uh, I guess the middle string pulls it up, the three corners pulls it down, and they kind of balance.
yeah.
yeah. So that's sort of how it goes. So let me try to see if I can draw a diagram for this. So let's say over here. Now I'm just going to sort of show a 2D version like this. And the 3D version is a triangle, so you just have to deal with one extra piece of string. Now, in a perfect world, this one piece of string is enough because this one piece of string is just sort of holding it apart. So this prevents it from going down. But again, moments exist, so this can sort of tip over this way. So now to prevent it from tipping over this way, what I can do is I can add a piece of string here. So now this piece of string is taut, it prevents it from tipping over this way. But now it can tip over that way. So I just add another piece of string here and extend this. Just add another piece of string here, and that prevents it from tipping over that way. Now, obviously, because it's a 3D example, it can also tip over that way. And that's why I sort of add a string here. But I'm not that good at drawing, so you guys are just going to have to imagine it. And this one is like making this is actually a lot harder than it looks. To be fair, I don't have a 3D printer, so I had to make it out of acrylic. And yeah, it turned out sort of about as well as you can expect.
Ooh, go back to your camera. I want to see it up close.
Right? Wait, I think, can you see it now? Like this?
How do we make this view big instead of the other one? Can you push something?
Yeah, it's in the top right
Oh,
corner.
wait,
There's
yeah,
a
I'm
view.
sure.
There's a view button that you can click
yeah,
in the top
okay.
right corner.
Yeah, cool.
All right. Does it look? Yeah. So
Beautiful.
now you should be, yeah. So this is basically the, yeah. So the thing is that I sort of cheated with this quite a bit. So like there's actually sort of like touching going on, and that's sort of what's keeping it together. I think I got like a few edge cases where without touching it was able to more or less stand still. I think it might not be touching anything right now. Okay, yeah, it's not touching anything right now, and it's just about staying. But the thing is that with this, because you know you need to do it very well, because this happens if you put enough force, the whole thing just tips because you have like different points of equilibrium, and it just needs to sort of like it needs to be very well done, and that's why I recommend if you're doing this, 3D print it. But yeah, that's sort of my terrible recreation of it.
Yeah, but I guess the smallest deformation will kind of allow it to move, right?
Yeah, exactly. So it's sort of like, yeah, you sort of need to, you're just banking on that slight area where over here it becomes more taut. But once it sort of escapes that threshold, then you just have everything that's just nicely chilling slack like this. So yeah, it's a bit of a pain, but it was a fun thing to work on. Although I probably shouldn't have been using my hacksaw so late at night.
It's actually kind of cooler to see the way it fails. I like that.
Yeah, so it's sort of interesting to see like to try and make these things for yourself, because you can sort of see from the back end of these and all. So now let me just sort of turn this around.
Maybe instead of using just one stick to the center, you could make it out of triangles, like a pyramid form. Then it would be more stiff.
Yeah, that would definitely be more stiff. But yeah, it's sort of yeah. So I sort of just wanted to make it more like that, to have that like magic. But yeah, that would definitely be a lot more stiff. So it's actually interesting. You have very precisely made versions of these. So it's called the impossible table. And actually, yeah, I almost forgot. You told me to show the other one as well, which I dropped in here, which is the impossible string. So like this. So I've sort of made it like this. Now, obviously, it's nothing impressive if it's lying down. So if you can sort of see the camera with me, you can sort of see how the whole thing stands just from the bottom. So it's also about having that constant tension. So with these kinds of things, it's really about, you know, it's quite impressive when you're able to work with objects that are very good in tension, but not so much in compression. And you can actually see examples of these, like with bridges and all, the strings that hold down bridges. Those are a great example of that. So it's sort of very cool where you can see all of these household examples, and then you can relate that to what's actually happening. So yeah, I find that quite interesting. So now I think, actually first, does anyone have any questions about sort of all of the mechanics which we did? This is basically like your sort of like first year college class? All right, great. So now I shall be doing what it would be like to actually bring it into a software. So now if I have this object over here, let me actually attempt to make it 3D. Remember, you have your whole sort of tricks to do that. Let's say like here, there. Mhm. Oops, I've drawn a lot of invisible edges. Oh well. Can just pretend that doesn't exist, and I need to pretend another one of these doesn't exist. All right. Yeah. So this is sort of like a 3D representation of a cube. So let's say if I actually like, let's just do something as simple as just sort of having forces along here. Now, let's say both of these forces are 5 gigapascals. That is a lot of force, but sure, why not? You get some real tension out of this. And you know what? Let's say this is aluminum. This is aluminum cube, and this is 2 meters by 3 meters, and this whole length is, so this whole length is 7 meters. All right, so all nice SI units. I mean, gigapascals isn't SI, but the Young's modulus is in SI. And it's, it's 66. One. That's the most common alloy that you end up working with. Wait, now this is it coming sideways for you guys, or is it coming straight?
Yeah, it's sideways.
All right, perfect. Now this is a lot more. Trouble for me.
If you can work like that.
Oh yeah, no, this is much easier. Earlier I had it like right in front of me. I sort of had to like bring my arms around it. Now this is easy. I just can easily move around. Yeah. So over here, let's sort of quickly do like figure out what the strains would be. So over here I have 5 gigapascals. So let's first write down Hooke's law. So you have this times this, and so you have 5 gigapascals over, this is 2 into 3 meters squared.
I guess that by drawing it like this way, you have these uniform deformations all over this shape. You are kind of assuming that this force is not applied to the center point. It's kind of distributed all over the surface, right?
Right. Yeah. So that is sort of what they actually look like. So it'll actually be a force
it's a lot
like
of
this.
small forces acting all over the same. Okay, then I get it.
Yeah. So in fact, if you sort of want force acting on a point, that is where you'll sort of have to bring in simulations, because that is too complicated to do just on your own. But you can actually do that with simulations. So
yes, but then it would kind of warp at the corners and stuff like that, right?
Yeah, exactly. That is what you'd see, and then you'll be able to sort of see that with your whole heat map and everything. So like let's say over here you have 5 gigapascals over this, which is equal to the strain which we're looking for into Young's modulus, which I said Young's modulus for aluminum is 68 gigapascals, but for the 6061 alloy it's actually 69 gigapascals. Now I'm writing units here because usually you don't get such nice cases. You would get cases in like forces in megapascals, you'd get like units in centimeters and all, and you'd have to sort of deal with all of that conversions. That's why if you're sort of ever doing like worked example like this, because let's say if I want to see the forces on this, it's a lot easier for me to just calculate it than to do simulation. But once it gets more complex, you'll see why simulation is so much easier. So over here, I can do that basic math. So it becomes 5 by 6 is equal to 69. All the units cancel out, so it works out nicely for me, and I'll get 5 by 6 divided by 69. And I do not trust my mental math enough to do this, so I will just sort of check on my calculator real quick. And that comes to 0.12 sorry, yeah, 0.012 approximately. And that means that if I actually want the deformation, I would just multiply that by 7. So the new length is 7.085 meters. So you can see that, like, even though I had such a large force, the sort of the change in length wasn't really much. So yeah, I think would this really be it for the example? So it actually won't. You still have to deal with the deformation in the other directions, and that's where this thing comes in, where to negative Poisson's ratio. So one thing that's really handy to know is that for metals, Poisson's ratio is approximately equal to 0.3, and for rubbers, is 0.5. So you can see 0.5 is quite a large number, and that is where you would actually see, like, let's say with your rubber band, why it sort of changes so much. What's really interesting though is that you have certain patterns. Unfortunately, it's not origami, it's sort of like a 3D printed pattern, but you have patterns where you have like a Poisson's ratio of 0. I believe you even have one where it's a Poisson's ratio of 1, although I'm not too sure about that. So you get these very interesting edge cases, and those are quite fun to work. So over here, let's say if I want to find epsilon y, I would sort of just take epsilon x, which is 0.012, and multiply it by negative 0.3. It's actually exactly 0.3 for aluminum, so it would end up coming to negative 0.0036, and that is where you'll sort of see. So over here now, and I can do the same thing where with epsilon z, and that is also negative 0.0036. So if actually do that into 7, sorry, into 2 and into 3 respectively. Let me first sort of check. So upwards is y, so that means delta y delta y is equal to negative 0.012, and delta z equal to negative 0.0072. And now I'm not going to bother with writing all those lines, but you can see how sort of this would shrink and this would expand over here, and you'll be getting a brand new cube with all of these different dimensions. So you can see, like, even for an example that was as simple as just me putting one force here, you had to do sort of like all of this working just to get it. Now, on the other hand, you would sort of even see something where you'll have forces on all directions, you'll have irregular shapes. That's something which you just can't do. So that's where you would actually put it into the software, and then the software would really sort of do all of the work for you. So let's look at how the software does it. So again, I'm going to sort of take this very simple example here. Now we are going to assume that this is some shape, very complex. It's not just sort of a rectangle. Uh, that's a disguise. So basically what happens is that it's actually not really, it's very often it's not even possible to solve it for everything. So what the software actually does is it creates a mesh. Now right now I'm going to sort of show a very simple mesh, which would just be a rectangular one. All right, so this is meshing, and this is sort of what it creates as a mesh. So over here, what it actually does is it may not be able to sort of solve it for everything, figure out what it's like, but it can sort of solve it for each point over here. So it can solve it for this point, for this point, for sort of all of these intersection points. And so on and so forth. I'm not going to draw all of that. Now, the thing is that actually you have different kinds of solvers, and a lot of them don't just stop at that. So a lot of them do the midpoints as well. So like, you have midpoints over here of these, and some of them may even do the midpoint of this whole thing. So that sort of varies based on solver. Now, the key thing to know here is that each of these points is called a node, and sort of each thing over here is called an element. So each box, let me just sort of roughly do that. So each box is an element, and sort of each point is a node. So this sort of again depends on your different settings and all, and I will sort of go through that. So over here you have your different settings, and you can sort of see with an element and a node. So you will obviously always have more nodes than you have elements. You can sometimes have the same number of nodes as elements, and this is sort of how it works. So obviously you have a lot more complex meshes. You will have sort of like hexagonal meshes and all, but generally meshing is something you don't need to worry about, at least definitely not with simple simulations. You just sort of need to have an idea of what your elements are and what your nodes are, because certain softwares actually have a limit on the number of nodes you can use. So like for instance, what is probably like the gold standard for simulation software is ANSYS. And ANSYS has a free version of the software that anyone can download. And that one has a limit of, I believe, 32,000 nodes. And that sounds like a big number, but it's really not. You sort of end up hitting those kinds of limits quite quickly. So it's sort of really important to be aware of what your mesh is like and how it works. So what your mesh does is it calculates exactly, it calculates the results exactly for this, and then it sort of spits out a result. But I think if any of you guys have seen a simulation study, and I will show a simulation study, you will sort of realize that it sort of shows continuous results. It can show you like sort of like a colored line, like, that color, those colors may represent like the gradient maybe, like, or it may be something like the deformation and all. And how does it really do that? So how it does that is through the power of, and let me see if I can, second, do this, right? Okay, perfect. Now it's sideways. So that means this comes the right way around. And it is the power of interpolation. Oh no, this is upside down. Oh well, I guess, right? And then I will just have to bring this over here. Okay, so it's through the power of interpolation. Now, interpolation, I'm sure this is something that you guys would probably be familiar with. If you've sort of like, done your graphs and all, interpolation is just how you connect up the points in your graphs. Now, unfortunately, you can't just do like a line of best fit because this is being done by computer. You need to have a sort of algorithm to really perform this. So obviously you have your very simple ones, which are linear. So like, let's say if I have these 5 points, your linear will sort of be able to do this kind of interpolation. So let's say, if I want to know what's at P 1.5, it just sort of looks here, it takes the point and it's able to give me. So because it's all defined in terms of different lines, different equations, you can end up getting an exact result through it. But this isn't necessarily the most accurate one. So you actually have quadratic interpolation, and that would be if you look at something like this. So this would actually be, so like for instance, over here you have 5 nodes and 4 elements. This would actually be 5 nodes and 2 elements. So you can think of sort of each line as an element. Now, obviously, I'm showing this quite simply. So this would actually be for a 1D example where you're only looking at things along X. In actuality, you'll be looking at things along X, Y, and Z. And that's where you get to graphs which are like, in very high dimensions, and you can't really visualize that. So that's why I just stuck with the 1D example. And over here, you can see you have these 2 graphs. And one key point that needs to be maintained here is because they're quadratic, you not only have to make sure that they're continuous, which means that both of these points are the same for both graphs. You also need to make sure they're smooth, and that means that the tangency is the same. So if you sort of want to mathematically describe that, it would sort of simply be here. Like, let's say if the red one is f of x and the white one is g of x, you need to make sure that the derivatives at point x3 are the same. So over here, this would sort of be your x3, y3. So you need to make sure that the derivatives are the same, and that ensures that these are smooth. So that's sort of your interpolation and how it's able to get smooth results. And this is sort of like, it for the theory behind it. And I think, right now I want to reserve some time for questions. And then, I think we have 45 minutes. So we definitely have the time where I can actually sort of go into simulation software to sort of give you an example of a very simple simulation. And then you can sort of see what happens in each step, what is the whole process required. And, hopefully I also don't mess up anything along the way. So yeah, I think, does anyone have any questions? Anything like that? All right, great. So I'm hoping that everyone understood. It's not that nobody sort of wants to ask a question. I'd rather go with that one. So let me open up Answers Workbench real quick. Now, I would personally not really recommend starting off with Answers. It's a bit of a very sort of like finicky software, but it sort of gives you the most clarity, and it gives you the most freedom in terms of what you can do with the software. So that's why I'm sort of showing the example here. So this is, you'll be using sort of like everything that's gone here throughout each step. All right, perfect. It started. I don't need to. All right. So here. So this is Answers Workbench, and over here I can sort of see that you have a lot of analysis systems. So imagine sort of like what we did in the first class, but you probably need one of those for each and every one of these. And static structure is probably the simpler ones. So that is what we're doing. One thing that's interesting to note is that all of these other ones are completely different, but you have transient structure, which is something that's quite cool to sort of think about. So let's say, I think like with simulations, let me actually stop sharing for a bit and talk about transient simulations. So, your static simulations is, let's say, like I have a ball, and if I apply 5 newtons of force to the ball, what happens? Now, transient would be the equivalent of saying I have a ball, and now if I'm going to kick the ball with, let's say, 10 newtons of force, what happens? So transient is essentially you dealing with forces that are constantly changing. Now, this may be something like the force sort of changing direction, which would be the case of a kick, or it could be a situation like, let's say, maybe you're dropping something and you're sort of having the actual value of the force changing over time. So that is something that is very useful for stress testing. So, like, let's say saying, like, it's very different to sort of slowly ramp up a force versus suddenly ramping up a force. And that's something which you can definitely see. It's not just felt like that for people, it's also like that for everything else. So over here, I sort of have a couple of different things. I'm really worrying about these first three, which is engineering data, geometry, and model. So first, let's take a look at engineering data because it's a relatively simple one. Over here, you sort of have your different materials. I'm not going to bother adding a new material, but over here, you can sort of see your different material properties. So for instance, you have your density, which is, I'm sure you guys are all aware of density. So you'd have density, you would have elasticity and all. Right now, this is assuming it's isotropic. That's why it says isotropic elasticity. You can actually change that. Then you would have your different yield strengths. So yield strength is sort of, if you go back to the diagram, that would be your fracture point. So the yield strength is the maximum stress it can take before it breaks. And that's why it's really important that we non-dimensionalize this, because otherwise the yield strength for sort of like a 2x4 block of steel would be different compared to the yield strength of, like, let's say, a steel water bottle. But now it's sort of the same for everything steel. So over here you have all of this information that gives you the structural properties of steel. I can actually add new materials. There would be, I can take materials that already exist, or I can create my own material and sort of give all of the values for it. Now that's not because I'm actually like creating a brand new material, but more so because it might not be available in the simulation space. So that's your engineering data. And now here you have geometry. So geometry ends up being another quite simple thing. Uh, Geometry is just sort of like, defining the shape of what you want to simulate. And that would be just, having that CAD model. So you can either upload something, or with a lot of softwares, you can create it using this. Okay. Let me just share this, which is now sort of the CAD software that ANSYS provides, which is basically a perfect. So, like I can create a model here. Let's say have a rectangle like this, make it 25 by 10 millimeters. And now I can go, let's see, I can make this.
One question, is this Design Spark you're using here?
No, so this is SpaceClaim, and it's sort of the design, the CAD modeling software that sort of comes with ANSYS. So actually, one sort of top tip with simulations is that, if your CAD software can do simulations, that's great, that's perfect, that sort of makes your life so much easier. But if you're using a CAD software that can't use simulations, one thing that I learned the hard way, and that was just spending an entire day completely failing to mesh, is when you're exporting, please always export in .iges. So I just file, let me just actually even type that out, because it's quite important. So it's .iges file. Yeah, so that's actually that's a really good question. I used Step and I regretted it because it led to a lot of topology issues, and I tried to spend a day solving them, and then I found out that no, IGS is just better. So for most examples of like simple geometry and all, Step should be more than okay. But yeah, when you're dealing with more complicated geometry, and I want to see. So I was actually doing a Workbench simulation on my drone, and if I would be able to share that, that would be lovely, but I'm not sure if Ansys wants to cooperate. So for now, I'll just be doing a very simple, I'll be showing off a very simple simulation of that. So yeah, unfortunately, it's a bit of a slow software, so you have to see, you have to wait a bit. It eventually does come. All right. Never mind, that is the one where it does not want to cooperate with my geometry. All right, there we go. That's come. Let me just share my screen real quick. So, all right. So now we're in mechanical, and we have this over here. Now, I actually haven't used ANSYS all that much, so I'm a bit sort of awkward with the controls. It's very annoying when you have to sort of go between different softwares, and they always manage to make sure that the orbit, the sort of movement codes are different in each one. So that's something to deal with. So actually over here, you sort of have the meshing tool. So over here, you can see a lot of different meshing things. So first and the easiest is just sort of the default mesh. For something like this, the default mesh is always good enough. It's nice, it's quick, it gets the job done. So over here, because it's a nice simple shape, it gave a nice sort of easy mesh. Now I can actually sort of change this up. So like, let's say maybe if I actually want a lot more refinement over here, I could actually click on sizing. I could select this face. So over here, this is not so much teaching the software, mostly just looking at like different ways we can manipulate a mesh. So I could change this size to like, let's say 0.00. Actually, that's 0.01. And now I could actually sort of update this mesh. And all right, okay, and leave this left. Moving part. Let's update. Right. That is a bit awkward. That's generally why you sort of don't try to mess around with this. Let me actually change the face sizing and actually just sort of do a resizing for the entire thing. So I can actually do sizing for this whole object to refine the mesh. I saw my error. I made it. Actually, I ended up making it larger. I forgot that this was quite a small object. So let's see. I think the default size was. And now I can update this. And yeah, so now you can sort of see over here. It ends up being a bit awkward because of how the highlighting is with that. But you can sort of see where over here I've changed the mesh sizing so that it's a finer mesh. And let's say over here I could change this to like, let's say maybe just for this face, and I could make that, maybe even smaller. And let's see, hopefully this doesn't take that long. Right? Now you can sort of see over here where compared to this, the rest of it, this one is a lot more refined. And you can see that a lot of these softwares actually have sort of soft behavior turned on, which means that, because over here it's so refined, it doesn't sort of suddenly go to normal, and it's sort of applied on the other faces as well to make sure there's uniformity. So that's sort of how it automatically has that. You can just disable that by making this hard. And now I can sort of update the mesh again. So, there's actually like a lot going on in mesh, and meshing can just be its own whole thing. But, it's there's a lot you can do. And sometimes you can just sort of slap on a default mesh. So here's where we actually get to the fun part. Although I've been told my definition of fun is very sad. And over here is actually where you can give all of your forces in. So let's say we actually want to simulate a compression load over here. So what's interesting is that if you sort of saw the diagrams for a compression load, we would have sort of put a force here and here. But what's different is that in a software, you could actually just put a support. So over here, I could have this be a fixed support, let's say right here. And that means that this stays still. And now if I add a force over here and apply this, let's say I can make it 10 newtons. Now that I've applied this force, that is the equivalent of me applying this force on both faces, because I'm keeping this one still. So the reaction force will always be identical. So actually in this case, you can see it's a tensile force. And I'm not sure if you guys can see the axes. Well, over here, because positive is this way, I would actually want to make it negative if it was a compressive force. And now it's a compressive force. So now I really have all of the information I need, and I can actually solve it directly now. So I can actually run a solve, and let's see, hopefully it's not too many minutes. I can actually see how many minutes there are. So we are going into statistics. Oh yeah. So yeah, you can see already just with such a simple example, we exceeded the 32,000 limit. So let me just change this sizing so that, it can actually run the analysis, regenerate the surface mesh. And now the nodes are much less. This is well below 32,000. So I can actually run the solution. All right. And just like that, it's been solved. So as you can see, nothing really looks different, but that's because, actually having a solved model is still a lot of work. So for instance, the simplest thing would probably be to look at deformation, total deformation. So you can apply a geometry selection. So let's say I could even just sort of apply it over here, and I could try and see the total deformation and evaluate all results. And it just shows me the deformation over here. So you can sort of see how it goes like this. And, this is obviously a lot more, this is, a lot more technical analysis. So it would be, you would end up having different results. It won't be nearly as linear. So you can see how the force is actually changing. And over here, it'll always be 0 because it's assuming that this point is fixed. So that's sort of showing how the force is propagating along. Obviously, it's a very simple example. So you'll get a very simple result. And, I could have changed this to, instead of scoping method being geometry selection, I can suppress this. And I can change this from geometry selection. Actually, I need to let geometry selection only. And I can select the whole body instead. And now I can suppress this. And evaluate all results. and now I can see sort of the whole result throughout the body. Of course, because I just applied a force here, it's very simple. But let's say I can go back in here to my structural thing, and I can afford to make this a bit more complex. So let's say if I want to, in addition to that, I want to actually add a force to this one. I want to apply it, and let's say this can be 20 newtons, and this is actually being a tensile force. And I can, right now I'm just making this all over the surface, and now I can do a solution, and I'll be able to get a much more complex result. So let's see, again, looks like that. And you can see with total deformation, you can now sort of see how the object's been bent, and you can look over here. One thing that's quite important to note is it's generally not the best idea to actually look visually at the sort of transformations, because these are usually exaggerated so that you can see it better. It's a lot better to actually look at the values. So you can see over here, it's 2.8 times 10 to the minus 7 meters. So that is a really small value, and that is definitely a lot less than what's being shown here. But obviously, if you just show that much, it wouldn't be visible. So over here, I can do that. I can even add sort of different solutions. So like I could potentially look at the strain energy in this. So strain energy by default, it's applied to all bodies. I can evaluate all results, and I can actually see the strain energy here. So this just shows the whole thing. And over here, it's again, because it's been such a simple simulation, everything is sort of coming quite grid-like. But later, when you sort of move on to more complex ones where you have proper interpolation and everything, that's when you'll get more complex results. In fact, if I move this resizing, let me just suppress this. You can sort of see the different things can change the results. Here you probably be minor, but there may be some slight difference in the results. Let's see. So yeah, over here you'll get these results. You'll sort of see it looks a lot more different. Now here, instead of being curved, it's a lot more straight because of the mesh. So that's why mesh matters. You get a lot more regular result like this now. So these are sort of like the things you can note. And additionally, you can even do like quite interesting. So like you can do probes, where like over here I can sort of see the values. I can actually define a probe. So over here, I can insert a probe for which I want. So let's say deformation. I can have it be this geometry, and it is sort of actually instead of geometry, I can have it be based on coordinate system. So let's say like at x equals 0.00, because this is all in meters, I have to make it quite small. Location. So it sort of ends up being a bit weird. You can actually define a coordinate system over here. That ends up being a bit annoying. So coordinate system, geometry. And over here, sort of it creates its own origin based on the geometry, or like let's say, would have it offset. Fine. So like with this, you can actually change the values. So let's say maybe with this, I want it to actually be 7 here. So I can change all of this to maybe 8, and just sort of have it like that. Now I can change my probe to be defined by coordinate system, and the location is this one, which is just named coordinate system. And now I can evaluate the result, and I can figure out what the deformation at that point is. So you can see it's sort of like the maximum and minimum values of the deformation. And obviously, again, when you get into more analytical studies, this is really what is useful. So you can see these values, and then also with probes you can easily sort of see where the max and min is, and over here it corresponds to this, and you can sort of get you can get like nice results and all, and show that. So yeah, I think that's sort of really largely been what I've wanted to cover here. And I think the rest of the time we can sort of leave for any questions, or if we have more time, you guys can maybe suggest a study but it has to be relatively basic that I can do in 20 minutes. But yeah.
A quick question. So did you try any of open source finite element analysis software like FreeCAD or something?
Yeah, so actually I've only heard some stuff about those softwares. I've heard they're actually pretty good. But yeah, I have the lucky opportunity of being a student, so I'm able to get free licenses for a lot of softwares. And yeah, that's why, like, for instance, it was a bit unfortunate. Like, originally my workshop was actually going to be on generative design in Fusion 360, but then a couple of days after my proposal was accepted, Fusion 360 just sort of nerfed all free accounts so that you couldn't do it anymore. So I was unaffected because I had a student license. But yeah, that's sort of the unfortunate thing with with other softwares. Yeah. I think your free softwares are definitely, like the open source ones, are definitely a good way to go. And I think they will certainly develop a lot more. But yeah, I can't personally comment because I haven't used it, fortunately.
Thank you.
So, any other questions? Okay, so I think, there are any questions, I can sort of answer them as they come. Or otherwise, do you guys have sort of any relatively simple study that you might want me to attempt in the next 20 minutes? Or I think,
I don't know, maybe breaking of a stick.
That's super brave.
let's see. All right, so I'll try my hand at that. That sounds like a fun one. So let me close mechanical. I think it might be easier if I just share my whole desktop. So let me do that, and I'll open up Workbench. So over here you can see sort of like I got everything. I got the whole model setup, solution results and all. So let me just sort of scrap this. All right, so I'll create another static structure. Let me create new geometry. Now, unfortunately, with this, I don't think you'll be able to sort of see the snapping, but you'll definitely be able to see the deformations. So I guess you have that. So what I'm going to have to do for this is a rectangle. First of all, I need to make it quite long and thin. I wonder if I could actually measure the dimensions of this thing. I have calipers in my drawer, I think. Correct. No, I don't. I will have to settle for a ruler. So thickness comes to about 0.5 cm, and we can make this about 10 centimeters long. So that will be 5 millimeters. Just dimension this to be, so it's at 10 centimeters. So that can be,
Can't you?
uh, 100. Or I could actually make this one, and I'll actually pull this out to be 50. And then see if I can this stitch here. Oops, that is not okay. Alright, there we go. And let's hope that these come as two separate bodies. So then what I can do is I can actually sort of constrain the center part so that you can sort of get a bit more of that snapping action. So over here, keep this 50. Ah, okay, I see what I should have done. Now when I pull, I think, sorry, I'm not sure. Okay, I think that's good enough. Now I can exit space frame. And now let's open this up in mechanical. Then, yeah, that's the unfortunate thing about basically any simulation software. You have to twiddle your thumbs for a bit. Right, there we go. Okay, so it is here now. Let's see. All right, this is looking pretty good. And so first, let's just slap on the default mesh. Really nothing fancy I need to do for that. Right, yeah, that looks good enough. Let me just check the statistics. Yeah, I can actually afford to refine that a bit. So, let's see if we can do some basic refinement. And now let's update the mesh. All right, that's much better. So yeah, that's a lot more refined, and yeah, my nodes are well within the limit. So now what I can try and do is here, and first of all, I will add a fixed one. Okay. Alright, yeah, I think I'll just have it be a fixed support. Right. And right here with force. I'm going to bring it over here, apply that, and instead of it being defined by vector, I'll actually make it based on components. So let me see what my axes are. So I would want this to be in the x component. Let's make this 100 because I realize now that this is made out of steel. I can actually try and change this real quick. Okay, I can change this to oak. This is something which I should have defined earlier. That's fine. It can be a steel one. Why not? So I can do this, and that should be enough. But let me try something a bit fancier. So I'll apply this geometry, and I would want this to be direct, and let's make this 100 newtons, negative 100 newtons. Just double check. All right, let's see how that works. Let's put that on a quick solve. So what is that? The deformation is very large. All right, the deformation is very large. Sounds like good news. All right then, and let's just quickly evaluate this. Yeah, so it says that the deformation otherwise is quite large. So you can see the deformation actually comes to 0.249 meters. Now I wonder if there's some way to sort of see the actual deformation. I think it's. I'm sure there's. I'm sure there's some way to see the actual deformation, but I am not aware of it. But as you can see, the deformation actually comes to sort of 0.249, which is quite interesting. There we go. It's showing auto scale. It's it's not giving me the option to take the actual value. How unfortunate. So yeah, this is it's not the best looking, but this is basically sort of what your snapping simulation would look like. Unfortunately, with stuff like ANSYS, you won't really get your super dramatic results. You're going to have to realize that if this is moving up 0.249 meters, it will not survive. So yeah, there are other softwares which I think, like, some of them may give you that snapping, but it's it's quite hard to get. But you can sort of tell with the deformation that yeah, it probably would not survive. So yeah, I think anything else? Otherwise, that's sort of, I really hope this session has been useful.
Yeah, it's a good overview.
All right then. So yeah, I think if anyone has any questions, we can answer those. Otherwise, is it is it okay if we end like about 10 minutes early?
Yeah, I think that's just fine. Anyone else have questions?
I think it was pretty clear to me, the presentation, so I'm fine with this.
Yeah, say thank you very, very, very much.
Yeah, thanks a
All
lot.
right. All right. Thanks a lot, guys. This was a really fun experience, and I hope you guys also tried the Mirafold. That's always that never gets old. Just
Cool.
I could do that all day.